Let me start with the question. When I was asked once, people who know me for a long period of time, and they asked me why I stopped starting my presentation with jokes. Usually I started off with jokes, and it was typical of me. Now I don't do that because with that I can't save some time. And by the way, I'm writing a book on utilization of the technologies, and some jokes are being accumulated there. So I would like to leave it and not to spoil. But people are back from the break, so before the start of my presentation, I would like to tell you a couple of more words. We dedicate this webinar to Altula, and he has a particular attitude to jokes. He had an incredible sense of humor, and his reaction to the jokes was a good one. And once in Petrozavodsk, we read a presentation, a report on jokes which are used in trees, but he forgot them all the time. So every single day you could tell the same joke to him, and he was laughing. And we were once in the city of Penza, as there was a workshop, and Archula sometimes had presentations and speeches, the trainees, and Slava Yefremov, he taught about geometric effects by using the ball-sized structures, and the indicator of geometric effects was used back then. So Slava was quite a boring person, I mean, with his speech, and people started to doze off. And then he told, do it urgently, just add some jokes, otherwise people are going to fall asleep. And I was so shocked. I'm not ready. Then I'm going to do it. And the previous night, I told him a joke, and he liked it. It was about Jesus Christ, who was working on the surface of water, and he was informed that one of his disciples, namely Thomas, and the Jesus Christ said to Thomas that he shall work not on the water but on the stones, just as all the rest of the apostles. Anyway, then he was asked, what does it have to do with all those balls, all those technologies? Because there was a dog who was called a ball. All right, so let us begin. And now you see my first slide, and you see the gentry's representation among two major directions in terms of trees methodology, and the whole webinar of today is dedicated to methodology development from initial ideas and postulates of Altula, and the square on your left is the classic question how to find the right idea to solve an initial problem. And you see also the dots above or below these squares, these frames, and this is what responds to this question. They are resolving contradictions, arrays, standards, databases, etc. And they are all the tools which were developed by Alcella together with his students, and then the development went to two directions. And the upper one, I called it as for the business, for the societies, how to solve a specific task, and the next one, how to find the right task, so how to find the right task which shall be solved. And then the next step is about the system. Was the system chosen correctly? And eventually, the frame on your right in the top, how to find the right goal to be achieved. We do not solve tasks today. How many tasks have you solved? No, we don't solve any task. We improve some specific system with the help of some strategic goals, which corresponds to the goals of the enterprises which produces goods or just companies. There is also the second line of the developments of trees. It is connected with the facts how feasible the solution is. If the very beginning Altruller, he postulated that when he was asked, Mr. Altruller, would you please tell me, trees gave us an idea, but what shall we do with the implementation? He said, well, it's not about me, it's none of my business, and this is the task and the job of the companies. But with the years and after some time later, it became clear that everybody has lots of ideas, and we need to have real products, which can be bought and sold on the market, new services, etc. And the second direction here of this methodology, it was connected with the fact how to solve the task and how to find the real solution, which can be implemented physically because many tree solutions they are based on theory and they don't work. The next step is how to find the solution which might be implemented. If it can be implemented physically, but due to some other reasons we cannot implement that, nobody is going to use it, and in the end, you see the frame on the bottom of the screen on your right, how to find a business impactful solution or technology. You see the two key directions here, and based on that, let us have a look. Where we see here the analytics and a very short history of this issue. Once Mr. Altruller said if we didn't have trees, the best solution would be to use analytics. And he was a professional, truly professional in terms of analytics utilization for different tasks. On the one hand, he practiced ARIES, step-by-step research. On the other hand, very often he found solutions based on his experience, education, and in the classical model of trees, there were two tools, and they used analytics. The first one, it was the utilization of analytics tasks. As usual, he was a real genius, and he tried to find a solution based on the type of contradiction, in particular the type of physical contradictions. If a physical contradiction in very different fields is the same, cold, warm, soft, hard, so the solutions might be similar. so that we could solve these contradictions. And some minimal details or statistics or data were accumulated. However, this tool was not developed, and there is a simple reason for that. In order to develop a tool, you need to have enough data, enough statistics, not 10, not 100 examples, but we speak of thousands of them. And Algela used statistics, patterns, the history of techniques with millions of units in this database. And for physical contradictions, there were no statistics. Nothing was published, there were no base of the physical contradictions. That's why this tool was not developed. And it can be a very interesting topic for a researcher, for the developers, just to write a thesis. And in fact, this is the great provision of Mr. Altula, which was not developed due to certain reasons. The second tool, I can call it as the biggest input of Altula to the general theory of technical systems. This is the law of technique development. The idea was different technical objects, different appliances, technologies, etc. They are developed due to certain laws. And if you are familiar with these laws, you can understand how this engineering process and systems work. And you can use these analogs in order to solve the tasks and in order to maintain the progress for the further stages of the engineering system. However, there was a problem, and how to resolve these contradictions of the laws, some particular mechanism of these laws, like monobipolar or monobipolar. This was the fundamental direction of the development. They do not give specific technical or engineering solutions. That's why to use them as the tool for finding the solution, it can be done. However, it's so difficult. One needs to opt for specific tools. If we speak of a law as the means for solving a task. That is why this direction, this idea was a strong one. And when Mr. Alchala initially he stopped his activity due to severe disease, and then he passed away in 1998. But the development of this direction was in continuation, and there were new tools, entries in the course of these 30 years, and they were developing this direction in terms of analytics, application, and trees. In 1990s, by my colleagues and me, we developed a tool dedicated to the engineering system evolution connected with the function-oriented search. It was about functions, and we postulated that if the function is the same or if the function is similar in different fields of engineering or human activity, that means that the solution for the solution is going to be resembling as well. And you or one can take one solution from one field and transfer it to another field. And This tool was developed in the last 30 years. It was intensified. There were algorithm and statistically, or at least in our company Gentries, we utilize arrays, and our main tool is the functional oriented search. When you prepare the function, which shall be corrected, which shall be improved, then based on some rules, you find the fields of the technique, and this function is much more important rather than the field where you are. And then you have to go back to a specific database based on some physical contradictions, and there were millions of them, and there might be millions of contradictions really, and typical contradictions. There are several hundreds of them, and we created a specific database in terms of typical solutions for typical physical contradictions. Today we have such a tool, a powerful tool as AI, and if the task is clear and correct for AI, it searches it much quicker, and it follows specific rules, and it also provides specific solutions how to solve this task. And today, so this is what everybody knows. This is a way how to use functional analog, functional oriented search. It's popular today, so I shall not promote it here because everybody knows, everybody utilizes it, and 90% of tasks they are solved with the help of functional oriented search. But I would like to dwell on another topic today. This is what was created at the beginning of 2000, and everything started with a thesis, master trees, by Mikhail Geshman, who lives in Israel. I was his supervisor when he was writing his thesis, and together we proposed to find a new method for analogs. But first of all, what were the disadvantages of the functional-oriented search? There were two of them. First of all, that's the functional analogs only are used, but there are other types of analogs, and this is what was used in the new tool. And the second disadvantage was that, well, it could be regarded as the advantage from another field to some specific solutions. And it is about the ready-made technology, ready-made components or material. And so this is an advantage and disadvantage, and it's clear why so. So it is the disadvantage because this tool didn't give any advantage. I mean, here we face different laws, and in the law there was prognostic, powerful efforts in see some concrete details in the functional-oriented search. However, it fails to prepare some forecasts and provisions. So this method was created and it was called as the parallel evolutionary lines. And this is the methodology, I believe. This is a combination of utilization of advantages and functional oriented search, and it allows to identify not specific targets but to find specific trends and to transfer that to a specific system. Not just one solution, but this whole trend. Let me add a couple of more comments about the open innovations, because once it was extremely fashionable to speak of open innovations, and this approach was prepared by Henry Chesbrough, an American professor in the 1990s. And basically, his idea was that not try to solve your own task. Somewhere in the world, there is the solution for your task. This is a great idea. Just need to find somewhere the solution and to adapt it and then to use it. Sounds wonderful. And Dr. Chesborough, a great provision and true. Almost every single task has an analog in another field, and from there you can find a ready-made solution and you can transfer that to your own field. And unfortunately, Professor Chesborough did not specify where to find it and how to find it, and later on it was developed. First of all, by the help of the functional-oriented search, which provided with specific algorithm where to find these leading areas for engineering systems and how to find specific and technically oriented solutions. On the right, you see the systematic innovations because initially they were open, they did not have a system. Companies just published on the website their problems and they hope that somewhere in the world, university would address it and would come up with a solution, but it didn't work out well, and the companies which were focused on open innovations, they fail, but they are the systematic open innovations were proposed and they unite three types of knowledge. So that you can find solution, you need to have specific expertise where you work. If you are in the food processing industry, you need to have enough knowledge and expertise there. Or automotive industry, the same approach. Then you need to get to know the right methodology. And number three is the worldwide knowledge collection. It was not a request, even with the help of the AI. It has the access to all the published sources of information. And how to involve these giant machine, how to utilize these millions of inventions, thousands of physics effects, thousands of chemistry effects or biology, etc. How to reach the correct points and the trace approaches of the functional oriented search with the evolutionary lens. It helped to develop this information and it transformed that to an effective means of solution of specific problems, and it was also helpful in terms of forecasting the few further systems. And currently there are four types of analogs. Number one here on the slide is they are the parallel evolutionary lines. This is a problem-solving tool to specific tasks, but at the same time, this is a tool for different types of forecasts, long-term and short-term forecast. And you can also identify the main parameters of consumers. Additionally, there are no parallel evolutionary line. It was analyzed, it was identified based on analysis in many systems. And based on our experience, just in our company, Gentries, we completed over 1,000 of innovational projects. I do not mean that we sold it as. No, there are over 1,000 really improved technical applications, services, etc. And in every project, there might be dozens of that. So we identified four types of analogs. One of them, functional analog. The systems in different fields of activity, they can have the same or very similar function. The next type of the analog, the analog in accordance with the principle of action, they have different functions, but the principle of action, biologic, physical, or geometrical, etc., any fundamental principle for action is the same or is very similar, and it is enough so that the analog can be transferred from the leading field to the initial field of the task. Number three, they are the analogs based on the property. They have different functions, different action principles, but they are very similar in terms of their parameters. And we can also transfer here the analogs from other systems, from the leading systems in particular. And number four, probably it's so unexpected. And I'm going, of course, to show you the example so that you could understand better. This is their resemblance in terms of application or market niche. Their systems are absolutely different, nothing in common. They don't have the same functions, they don't have the same principles, no parameters, no common parameters, and they are aimed at the same category of consumers. And interestingly, that in this case, we need to identify the leading area and to transfer from there some of the trends. And let me remind you that in the parallel lines of the evolution, just do not transfer the really main decision, but we have the whole trends. And yeah, this is the whole theory. Of course, there is the algorithm of the parallel evolutionary lines, but I would like to show you a couple of examples, and I'm going to start with the functional analogs, functional similarity cases. So, example one. We collaborated with the company, which was the manufacturer of water distribution systems, water faucets. We use them on daily basis in the kitchen or in the bathroom. And if we speak of the functionality, let me just show you on the whole screen. Can you see it well? Yes. So let's start with the function. We chose this water faucet. And what is the function of it? To distribute the water flow. This is function one. Its volume as well as its temperature. And the same here in the research. In order to find the analogy, we need to understand that we deal with water. We need to regulate the temperature of water as well as the speed of the flow. Then we formulate the general function of that, how to control and how to manage the moving objects and components. And according to certain rules, we opted for some leading systems in this area. And so one of the system is that in the car, the managing system of the glasses, this is the same principle, and we received certain trends from the manual manipulation, from touching the handle. Then there was the electrical activation when you push the button and the glass, the window goes up and down. And today's models, they have sensors activation.
When you don't need to turn anything, this is relevant for contemporary, for modern models. When you don't need to use any handles, it just closes automatically when you press a button. Like Igor has mentioned, you don't need to wave or to move your foot because the system can feel your presence itself. So this is how we identified the generalized function and the area itself. And then after that, we looked at what's happening. We saw that these control systems, window control systems, we started from the manual operation, manual actuation. Yes, we use water faucets to control water faucets, operate water faucets manually. Then after that, what we had in the cars, we had electric actuation when we use buttons, electric buttons to control window opening. Then we compared that to faucets. We worked with Murin, an American company. It turned out that they already patented and designed. We didn't know about it, but we told them, you know, that the next generation will be the electrical operation when we don't use any handles, but we push buttons. Yes, well done, they told us. We have already done that. We have already designed it. What's next? Then after that, the next stage was sensor actuation. So we predicted that the next stage in the development of water faucets will be when you just place your hands or move your hands to the right or to the left or up and down, and with that you control the flow of water, uh, actuating the flow of water, switching it on or off, closing it or opening it, and also you can control all the volume of the water poured out of the faucet and its temperature. So with that, we managed to patent these modern faucets and put them to the market. We found not just one solution, we identified the whole trend out of all that. Example two. This is the second case study, which is an example of a functional analogy. This is the case of a company. This company produces construction equipment. They manufacture, they make excavators, tractors, and other types of equipment. An excavator excavating a trench or a pit, an operator working there, he does not know what's in the soil, what's in the ground, so you can break the excavator handle, and indeed this is really a problem for the construction industry. It's very hard to identify what's there inside in the ground because you can easily break the scoop of the excavator. And of course, it's good to know what's inside before you excavate. The function is you need to understand, identify the object inside in the soil, and then identify what we found there, whether it's a pipe or a wire or a plastic piece. So we can then generalize a function. So we forget about excavators, we forget about the specific feature, the specific area of our customer. So we need to have this see-through mechanism. So we need to be able to see through the ground, through the soil, through opaque objects. This is the generalized function we derived. Then after that, we come to the stage of identifying leading areas. How do we find leading areas? So before that, before we had dedicated databases, but now we can use AI for that. We found several leading areas. We found the visualization inside a wall in construction system. For construction, we identified geophysical exploration, for example, finding natural deposits underground. And there is one more, which is quite a remote area, maybe far-fetched medical investigation of the human body when we do medical tests or examinations. So this area turned out to be the most advanced, and we chose it. We selected it to be the leading area for replicating the trend to the construction equipment. What we found in medicine from physical methods of seeing inside or seeing through, we have the next stage there, which is image processing, followed by a number stage when operations are performed. For example, a surgeon working on an operation can see what's there inside a human's body without cutting. Without cutting, they already see through the human body. So this is the approach we selected. So we took two systems. We took medical visualization and also the system of underground obstacle, underground object detection. In medicine, so we have this X-rays, ultrasound, and other solutions which are well known. What do you have in construction? Those are like fresh inventions. These are dedicated penetrating radars, electromagnetic induction solutions. This has appeared recently. This is again what we had as a request from our customer to design it. The next stage in medicine, image processing. So this is CT scan, MRI, US scan, etc. So these systems in medicine are very well developed and well spread. In construction, on the other hand, the only thing we could find is the so-called seismic tomography and holography, which was only available in publications while there were no live solutions at the moment when we implemented the project for the customer. In medicine, the next stage involves guidance of surgical tools when a doctor can actually manipulate surgical tools inside a human's body. So this is how this interaction happens at this level when you use these surgical tools, so this field vision through the human body. And we didn't find anything similar to that in construction, even in publication, even in research. So we suggested having that, and our customer patented such a solution. They called it precise guidance of excavators when an operator of an excavator can see and manipulate the scoop, looking at what's there inside the soil. Well, that was first theoretized, and further it was patented and implemented. I'm looking at my watch there to keep the timing. Let us now look at these action-oriented, action-focused analogies, and with that I'd like to illustrate what I'm saying with an example, with a case study. We worked with a customer making cosmeceuticals, for example, soap. They made soap. Our customer's company came up with a new type of soap. crystal soap. Like ordinary soap we use have a number of drawbacks. It dries our skin. It's not that soft very often, and it's not good to soften, to humidify skin. So, and again, you need to add some expensive additives. So that's why our customer came up with a new type of soap, which is crystal soap, which is very soft, transparent, and it makes no harm to the skin. But its drawback is this is brittle, like other crystal objects. It's brittle. When you wash yourself, it's not relevant. If you like drop it on the floor, it can break. But when you make it, it becomes a real problem because standard soap is made in a way that makes it simple to design it and to make it. And there are highly performing technologies to produce soap. They are out there. When it comes to this brittle crystal soap, how can we make it? Customers tried to come up with any solutions to make this soap, maybe using some molds for that. They tried to create different molds to create different shapes of the soap. So they uh, took the liquid substance and they used different forms, different molds to then crystallize the substance and make the crystal soap. The performance of the process was much lower compared to standard soap production. So you need to put the substance to the mold, then wait when it crystallizes, when it becomes solid. And the goal was to make this work with higher performance, increase the performance two or threefold at least. But we managed to do that, and we managed to increase the output tenfold. Let us look at the analogies. Now, what did the crystal soap manufacturing process look like? So this liquid soap, they put it in the forms and the molds, then it took some time to solidify, then it was extracted and packaged. So the most challenging operation stage there was the solidification of the soap, because this solidification process in the mold, it starts from the top, from the surface. So from the outside, they had this solid substance, while inside it was still liquid. This solid core, this solid um, structure around the soap, it actually was a thermal, it had a thermal isolating effect, and of course it was very hard to overcome this effect to make the whole piece solidify. So now let us look at the analogies. Action principle, crystallization from liquid form. So this is the principle, the action principle our customer selected. A leading area. Now this was very easy to find the leading area. Again, millions of tons of metals are manufactured through crystallization of liquid metals and solidifying metals to create metal products. What is the trend that we identified? We started casting into sand molds, then after that water-cooled molds were used. Then after that, there was a new approach, new technology, which was called continuous casting, when this process was continuous. And then this was followed by the most modern technology, which is 3D printing. Now, this 3D printing of liquid metal substances and creating solid metal objects, so solid metal products. So we selected this technology, so you can take a trend and use it for your system. But if you want to select a specific solution, you can find one and find the most efficient solution and try to use it for your object. So we selected this continuous casting to be our selected technology that was relevant for metals. And we created this continuous casting in a water-cooled tube technology. So this casting here is not about having and casting these molds. This is not about using molds for that. This casting, continuous casting of metal, that is the selected technology that we use. Now let us look at the example with the soap. Here we see this technology, which is continuous casting, so we have it, and we still face this challenge with this solid edge of the piece. So we wanted to understand how we can break it, how can we avoid it when we apply the continuous casting process. We formulated this method, this action principle. This action principle is used for mechanical stripping of metals, and they just remove these cores, these edges mechanically. So that was what we looked at, mechanical stripping approach. Leading area was metal processing and cleaning of complex shaped products. And then after that, we identified a trend here from cutting of some bumps on the surface of metal objects, followed by abrasive wheels, followed by wire brushes, then sandblasting, and followed by ultrasonic cavitation, chemical etching, and laser cleaning. Laser cleaning. So this is the trend, the evolutionary line of metal products that we identified. We selected ultrasonic cavitation to be our technology of choice. Abrasive wheel and wire brush was not efficient enough, while ultrasonic was the technology with desired performance. Now this is the technology that we came up with. I'm trying to speed up to be able to be on time. Now what we came up for our customers, so we took this liquid soap, which is fed into the pipe, into the tube. That is the molding pipe with a source of ultrasound. This ultrasound has two functions. On the one hand, it continuously breaks this edge on the surface of the piece of the soap, which solidifies all the time. This ultrasound also creates these spots of crystallization within the piece of soap, like what we had with the molds. With this process, soap solidifies in an instant. So like a miracle happens when you turn on ultrasound and it crystallizes rapidly. Then after that, you got the piece. Then after that, you melt it from the sides to make it smooth. Then you pack it up and send for sales. We used those parallel evolution lines twice, and we came up with strong solutions through those respective trends within this example, within this case study. A case study on the use of analogies on similarities, on feature similarities. Another example, our customer producing detergents for washing of clothes, so they made those laundry detergent capsules. So you put a capsule in the washing machine with dirty clothes, and then this capsule melts, and then this detergent is distributed across the clothes inside the washing machine. Now, what are the features of a product? So we looked at at its form factor and its aggregate state of the material. So this is some solid capsule. Inside this capsule, we have liquid material. Now let us look at those leading areas. We found a couple, we found two leading areas, and we selected one out of the two. So this is the per oral drug delivery to human organisms. This is the leading area that we selected. What is the trend in this area? What we identified from patents, from publications. So we start from powder, then followed by tablets, followed by liquid or semi-solid dosage capsules, so made of some material that you can melt with your saliva. So this is what they use most often today. It's either tablets or those soft dosage capsules. But also we have functional capsules, which people can make. Actually, it's a capsule which can contain any drug, so this delivers cumulative effect when you have several substances inside one capsule. Now let us look at our example for our system. Powder, also for the washing. It's all the same. It all started from powder, then followed by tablets. In laundry detergents, we had the same tablets. So again, those tablets were used also for laundry detergents. That was followed by capsules with soft content, and it's all the same. Our customers made these capsules, disposable capsules, when you put it inside the washing machine and you wash your clothes, and then you wash. Now this stage of functional capsules. So these functional capsules where you can put those medicines, those drugs you need, prescribed by a doctor in the dosage with the desired, with the needed dosage. We didn't find such an example in the laundry detergent domain, so we suggested our customer use such technology. For example, for hard to wash clothes, you put one detergent. For something else, you put a different detergent to the capsule. Now and again, you can add different ingredients. For example, you first use something which removes stains, and then after that followed by the washing itself. Target delivery is also possible, so you can deliver those ingredients where they're needed. All this was patented, and now we expect this new product in the market, this new line of detergents coming up and entering the market. My last example, which is of course an unexpected one maybe, so this is similarities based on market niche or field of application. We worked with a company working on in the field of producing jewelry, jewels made of glass crystals like Swarovski. Our customer actually is a competitor of Swarovski. When we worked with this company, they asked us to make a forecast. So you remember me speaking about the evolution line, so which is a very good way to forecast. Now, what's next? We can make us forecast and understand what is going to happen looking at leading domains. So here we used the market niche analogy similarity. So and again, what is the market niche? What is the application field? Those glass crystals. People buy these crystals. Those people buy them who cannot buy diamonds or sapphires because they are much cheaper. But of course, Swarovski, it is still glass, which we call mountain crystal, which is much cheaper than diamonds. Maybe we could find an area in which people need to have these cheaper products and they're ready to pay good money, but they want it to look like a an expensive product. We found such a niche. This is furniture and food industry. And I'd like to show how this trend was transferred. So what trend we identified? So we have expensive materials followed by combined materials, which combine both precious and cheap components, followed by other materials, so the refined materials, in which we don't have any precious elements, but they are chamfered, they are processed in such a way that they look like a real one, a an expensive material, followed by imitated materials or fakes, basically fakes. So this is what we have in furniture and food. This is what we identified. And we also identified the key consumer parameter for these glass crystals. So we wanted to make this imitated crystal that would be imitating the glass crystal. We wanted to make it look similarly and shine like a real diamond. I've always ran out of time. So again, we started from this trend, having this expensive wood and furniture, followed by cheap wood covered with veneers. For example, this very thin layer of costly coating, followed by stained cheap wood. When we use stained cheap wood to put it on the surface of wood, this is followed by plywood, which is imitated materials. The same we have in the food industry, expensive meat, followed by meat plus offal or subproducts, followed by sausages, which made purely of offal and additives. And also we have fake meat, tofu, and other protein-based products, which are much cheaper than meat. Looking at our crystals, expensive diamond, glass crystal doublet. So these are the doublets made by our customer. Those are combined materials when we have a very thin layer of this mountain crystal, and then inside we have a much cheaper material. This cheap glass inside. Now what else? What's next? For crystals, these refined materials, and this is what we came up with, and our customer patented this one. It is actually a cheap glass product. It's not diamond or mountain glass. There is this glass fibers that are inside this product. They are very cheap, and this is then lighted. When you put some light on it, it looks like a very expensive gem. And all women like these prototypes, but they cost really cheap. Then after that, we forecast the next stage here. Looking at these ones, we do have some with those optical fibers. The next stage will be the hologram, when you don't have an object actually physically on your hand, but there is this hologram that can replace it. It's not yet patented, but it's already available. So we developed an algorithm for the appearance of this application, so I don't want to list it here. We created a number of forecasts for our customers, focusing products for them, and forming those patent umbrellas for further to be products and technologies. And with that, I'd like to stop to save some time for questions. Now, conclusions.
And the analogs, which are preferred by Alchala, and this direction is still a continuation. And if somebody from the audience is interested in that, there are several topics for the further developments of the analytics entries, and we can recommend it to your research papers, or if you would like to become a trace master, it's a wonderful topic for your thesis. Now, I thank you for your attention. Unfortunately, we don't have any time for questions. That is why, Dmitry, you raised your hand. Just please be very short. Yeah, Simon, I love to ask you to reply to my question because I even wanted to write you. How can you translate into Russian the word features? Because it means some characteristics. There are functional components, there are functions. We have parameters or some quantities, but we understand what it is. But a feature, how can you translate it in the model? What is a feature? To be honest, a feature can be translated as peculiarity, for example, characteristics. Is it a parameter? No, it's not a parameter. Let me give you one example. Feature, they are the characteristics, and parameter is temperature, and heat conductivity is also a parameter. I do apologize, we don't